Thank you for introduction. Today I'd like to talk about the Kokkos-FFT updates. This is the team effort of the CEA SEGSA team and in collaboration with the Kokkos Squad team. So let me first introduce why Kokkos-FFT and who needs it. For example, there are many legacy applications relies on FFT in the particularly in the fluid simulation fields. For example, using periodic boundaries or for plasma turbulence. Actually, we are one of them, called G0 code, written in the right at the top. Because in this type of code has the intrinsically periodic along the toroidal direction, so we always need it. Another use case is probably having a Kokkos code and waiting to integrate some sort of the data processing with FFTs, like spectral analysis or low-pass filter and things like that. But who do not willing to get through the documentation of the different standard FFT libraries, because in the these have the different APIs, and also for the documentation it's not necessarily easy to read. So, but we like to benefit from the powerful vendor libraries, and we try to make it as simple as NumPy FFT. So our design is strictly following the NumPy design, just like it here, the same API as NumPy, but with slightly Kokkosified, increasing the, because then we have the execution space and argument also for the Kokkos views argument instead of NumPy array. The details are found in our JOS paper 2025. And recently we have released the 1.0. The key idea is as simple as NumPy FFT as first as vendor libraries. We support the 1D to 3D FFTs and up to 8 Kokkos views. And batch plans are automatically used if the view dimension is bigger than the FFT dimension. And the nicest thing is that in all you need is just preparing views, and you don't need to care about the complicated APIs internally. And it's much safer because you don't need to manipulate raw pointers. And you have compile time and runtime errors if there is some sort of invalid use case. And we support the non-experimental backend, including NVIDIA and AMD and Intel GPUs. We are currently supporting the contiguous layout only, namely layout left and right. And you can use both device and host execution space. We already use it internally, but in if you are interested, feel free to use this one. One test case is just in solving the typical and the two-dimensional as a global-Cartan equation using convolution with FFT. And the left top snippet shows our implementation using Kokkos-FFT and Kokkos, and the right top is just using Python. Of course, Python is simpler, but in the benefit is that in the lines of code is just in the 1.5 times longer compared to the original Python version, but it's not that complicated. And the performance gain is enormous because you can benefit from GPUs with a single code base. If you would like to use that without Kokkos-FFT, it can be much longer, and you need to use the macro to switching off the different backends, which is kind of not what we want. So, and this year we focused on the improvement of the distributed FFT part, because some people want it. And scientific computation, and there are a couple of cases to rely on distributed FFTs. One use case is the 3D-dimensional direct numerical simulations and at the top left. Another is the plasma turbulence, we are actually the ones. And also another example is the molecular dynamics like ramps. So actually there are strong demands to have the high performance but portable solution for distributed FFTs. Also, we need a good scalability. And this slide summarizes the existing distributed FFT libraries. And there are a couple of these, and most of them are focusing on NVIDIA GPUs. For example, 2D comp and FFT library is between Fortran and OpenCC, and it supports CPU and NVIDIA GPUs. And QD-comp, as named, targeting NVIDIA GPUs, cuFFT also. As far as I'm concerned, hipFFT is the only one that supports all the backends. And we are also doing it in the same way, but instead of writing the CUDA and hip and secret part by hands, we rely on Kokkos for simplicity, and also Kokkos-FFT for the FFT interface, so which makes the the code implementation significantly simpler. So thanks to Kokkos, we get the portability for free, and we spend more time for the something more complicated on top of this one. This slide summarizes the Kokkos-FFT distributed capability. The right top figure summarizes what we are doing. There are the prime classes, and this is shared means they're the embarrassingly parallel case. So the batch polarization only made in the batch direction, so you don't need to do some complicated MPI stuff. The slab and pencil plan just implies in the slab decomposition or pencil decomposition. And TPL plan is just in wrapping the vendor native FFT library, like cuFFT for example. Internally, and we computation effort is highly relies on Kokkos, and also for the FFT interface through Kokkos-FFT. And the communication libraries may be replaced with Kokkos.com in the future, but currently we are hardly implemented by ourselves and supporting the NICU and ROCO and 1CCL for each backend. And the interface is quite simple, I will tell you later. But then again, you only need to prepare views, and it's safer. We support all the non-experimental backends. Currently, and we are basically relying on the voice-aware MPI for all-to-all communication. The right bottom figure shows the pencil decomposition. The pencil decomposition means that in certain dimension, for example, in the green cube, in G direction, we have all the elements along that direction, but other directions are distributed. Same for Y and between blue and X for red. And basically in distributed FFT, we just transfer in between these different layouts. This can be easily achieved by all-to-all communication, and technically made by the other communication libraries like collective libraries. And we also have the strongly interest into the vendor native library support for cuFFT, and I also started to investigate rocFFT MPI for AMD, but it's not done yet. So API is quite simple, and the left top snippet shows the FFT for the non-distributed version, and you need to, as usual, you first prepare the Kokkos views and with input and output, and just pass it to the plan creation API, and just give it to the execute API to perform FFTs. And this way, and you can perform FFT on different views as long as view has same extents. The distributed FFT API is designed on quite similar to this one. The major difference is that you need to specify the input and output topology, and also for the communicator you are interested. So basically, and also in addition, the input views must be existing locally. So this is already distributed, and also we need to feed the input and output topologies. And also, this plan can be reused for both forward and backward direction, because internally we have the intensive memory usage for this one. So we need to reuse as much memory as possible. So the execute API takes the FFT direction instead of the plan API, which was the case previously. But it's not that complicated. So implementation details, we rely on the dynamic polygon feeds and to select from our distinct internal plan types. As I have already explained, it's basically just in our implementation, the shared and strap and pencil decompositions, and also for the TPL plan, this is an alias to the third-party library. And the core implementation is the all-to-all wrapper, and also pack and unpack routines, also transpose and the normalization. So these are the key components. Our key idea is just to make communications as simple as possible and do all the complexity on GPUs, because FFTs are basically communication banded, and we'd like to use the simplest and efficient with the fastest as well. So we just use a simple wrapper for the left snippets, and this is just in the simply calling MPI all-to-all. So it's quite simple. Since we have some expertise on GPUs and all the complexity is handled there. So pack kernel is significantly more complicated because we'd like to do all the complexity there and makes communication as simple as possible. And here, this is basically parallelized with the Kokkos-MD range policy. And we spent a bit of time to improve the performance for this one, which is talked by Harit next. We developed the benchmark application using the 3D Navier-Stokes equation in the free spectrum method. The one unique feature is the batched capability of this library. The rest snippet is non-batched case, and you need to do the similar operation for different velocity direction, U and V and W, which is kind of a bit annoying. But using the batch capability, you can just stack all the velocity into a single 4D view, and which significantly simplifies the implementation, as you can see, by comparing the different snippets. And this kind of batched capability actually, unfortunately, did not bring us any performance benefit in this test case, but there should be some very useful use case like the 2D batch distributed FFT in the delta F gyrokinetic simulations, which can be a major use case of these FFT libraries. We have measured the strong scalability of this Navier-Stokes code, and actually in the it looks like in the and from 16 GPU to 64 GPUs, it's basically 2 nodes to 8 nodes. And on MI250X, it scales nicely, and 800 scales less nicely because this is just because the communication bottleneck is significantly bigger in the MI250X. So in the end, the performance is roughly identical for all these backends. But in the just it scales nicely because on MI250X at the beginning point it doesn't perform well because of communication bottleneck, but that's all. And if you look at the breakdown of each part of the kernels, and all is the blue which is the most important one, and some computation one is written in the pack and unpacking is in the orange, and the 50 is green one. And actually in the as you can see, the all is most likely is the major bottleneck, and most of the cost is coming from that. And even in the NVIDIA and the Intel machine, in 64 GPU parallelization, 90% of the costs are coming from all-to-all, which is actually probably quite usual for this kind of FFT, distributed FFT. And this measurement is done before implementing MD range policy, so the pack and unpacking performance should be improved a little bit. And we try to investigate the device communication libraries for better performance. As a reference case, and we compare the performance with cuFFT MP. Actually, in there was a bit of complexity to use this library, so I made a good performance measurement on the 16 MPI case for the O2O, and actually in the cuFFT MP outperforms our implementation a little bit, but not much. So our implementation is kind of comparable. But in the for the H200 case, it's 30% or things like that faster than our implementation. So definitely we can have some benefit from using this library. And at the bottom of this table and all-to-all, you can see that in any architecture, roughly same time is used for the all-to-all, and other parts are less important. So in the end, we have almost the same performance on there. Actually, in the 624 MPI case, it's not performing very well because in this measurement is done before I found the solution to have to use cuFFT MP correctly. I mean, in order to use cuFFT MP, you need to pay attention to the CPU bindings, because internally it is relying on the NVShareMem, and you need to make sure that every process needs to access at least 2 different cores. So you need to carefully set it, and which is automatically set for the H200 case, and we have found that it is 30% more faster than our case, our implementation, which is good. And after finishing this measurement, I will update this slide, and when up in the Linux and the HPSF conference site, you will have the correct number for this part. So let me summarize in this work and and also for future work. So we have recently developed the distributed FFT interface for on top of Kokkos ecosystem, to have the performance portable and scalable FFT interface. And this is simple to safe and interface thanks to Kokkos, and I would say good performance on the NVIDIA and AMD Intel GPUs. And also, I didn't talk about it, but still keeping the reasonable performance on CPUs. A nice and unique feature is the batch capability support, which is not made by many libraries, and also for the vendor native distributed FFT library supports, and which actually outperforms our native implementation. The future work includes the better integration of the GPU collective libraries, including Niku, Roku, and oneCCL, and improving MD range. This will talk by Harry in the next talk, but we have recently done the optimization on device, so some of the performance should have been improved by that. Thank you for listening.
All right, are there any questions?
It's not really a question, it's more a comment. I think it would be great if you talk with Kokkos.com and you make sure that some of the interface you're going to do is compatible. They have some abstraction, to encapsulate the communicator and the other good stuff from MPI. It would be a shame if we are inconsistent between the different library.
Yeah, I agree. Just one comment is that probably we are not interested in Niku and Roku and oneCCL. We should be more focusing on NVShaman, and NVIDIA is using more like NVShaman rather than the Niku or Roku for better performance, and we have to consider that if it is compatible with Kokkos.com side, because I'm not sure they are interested in NVShaman capability.
Thanks for the talk. First of all, I'm not an expert on this field, so I have very simple, just naive question. So I heard that in case of FFTW or other Fourier transform algorithm, they get speed ups when the domain size is the power of 2, like 10 to the 10, 10 to the 12, or something like that. Is the Kokkos-FFT also suffers the same thing, or is it more dependent on the number of, for example, the nodes?
The nature of FFT libraries, and we are just wrapping the FFT libraries, so we have also the same feature, and it's probably 2 is the best. It's the simplest in prevent anyway. So, yeah.
Thank you.
All right, any more questions? If not, Harry, we can go ahead and get set up. And let's thank our speaker again. Thank you, Yuuichi.